Welcome, Math 13 students. We have some detail here in section 6.4, the Central Limit Theorem. So, before I get started, I'm going to point out that section 6.3 and 6.4 together give us the theoretical basis for inferential statistics. The reason statistics works really is because of the theorem we're about to take a look at, the Central Limit Theorem. So let me go ahead and share my screen. We'll get going. All right, the Central Limit Theorem, examples and theory. First thing I'm going to do is to review the Central Limit Theorem. It's wordy and it is subtle. We'll explore the implications, and as we do that, we'll introduce appropriate examples. So, there are some requirements before we can use the theorem. Number one, you need a population with a mean mu and a standard deviation sigma that you wish to study. Second, you need to take simple random samples of a given size n. So the theorem applies to samples of a given size, whatever that size might be. Now, when a population has a normal distribution or n is greater than 30, some nice things happen. The mean of the sampling distribution is equal to the mean of the population, so mu of x bar is equal to mu. The standard deviation of the sampling distribution, sigma x bar, is equal to the population standard deviation sigma divided by the square root of the sample size. And it has some very nice implications, as we'll see. The very nice thing is that the sampling distribution for x bar follows a normal distribution. So if I took samples of a given size, found all their means, made a nice little histogram, that histogram would form a normal distribution, or at least close to a normal distribution. You're going to see that. I have an extra credit exercise that goes along with the 6.4 material, and you'll see this happen yourselves. There is some limit to the theorem, though. If the original population does not follow a normal distribution, it does something else, and the sample size n is less than or equal to 30 on the small size. If those two things are the case, then the central limit theorem does not apply. But if your n is greater than 30, then the distribution is normal or close enough to normal so it doesn't even matter. This is a very powerful result. The actual population distribution does not matter. Go like this, like this, like this. You make a histogram of the means, and you'll see that picture. And this is also why a reasonable sample size is so necessary. There's also some subtle detail into the wording of the questions. Once we have the central limit theorem, questions on probability can include questions on whether a sample mean is either greater than or lesser than a given value. From section 6.2, questions look very much like this. What is the probability that a randomly selected score is greater than, lesser than, or whatever the case might have been? That's right out of section 6.2. In section 6.4, the questions will also look like this now. What is the probability that a sample mean is greater than, lesser than, or maybe between values? You can see the difference in the wording. A randomly selected score, that probability, or the probability that a sample mean, a whole group of objects, has a mean that is greater than a given score. Now, let's take a look at our first example. We know that IQ is normally distributed with a mean of 100 and a standard deviation of 15. So the first question is, what is the probability that a randomly selected person has an IQ greater than 105? That's the first question. Notationally, P of x is greater than 105. Looks just fine, right out of chapter 4. Here's the follow-up question. What is the probability that a randomly selected sample of size n equals 25 has a mean greater than 105? Notationally, this looks a little different. It's the probability that x bar is greater than 105. It's a subtle change in the notation, but it makes a world of difference in the type of question that is answered. Here's the first question. What is the probability that a randomly selected person has an IQ greater than 105? We're going to use a mean of 100 and a standard deviation of 15, and we're going to draw a picture first. Yeah, seriously, draw a picture. Ooh, that was quick and noisy. There we go, much nicer. So we want to find that area. That's the probability that x is greater than 105. I come over here to my calculator, second distribution. I'll pick number 2, normal CDF. The left endpoint goes in first. I said 105. The left endpoint goes in first, comma, followed by the right endpoint. Now the right endpoint is functionally at an infinity, 10 raised to the 10th power. Gets me close enough, comma. Now go the parameters, 100 and the 15. Close up the parenthesis, and now we're ready to go. So the probability that a randomly selected person has an IQ greater than 105, 0.3694 and change. If I take 4 digits here, what do I see? The probability that x is greater than 105, 0.3694. 369 to 3 significant digits. So that's your first question. The probability that an individual has an IQ greater than 105. Here's the follow-up question. We want to know the probability that a randomly selected sample of size n equals 25 has a mean greater than 105. Now the parameters are going to look a little different. Well, I'll use the same mean, mu of x bar. You can see the change in the notation. For the standard deviation, I'm going to use 15 to the square root of 25. And no, I will not simplify it first. I'm going to leave it just like that. Let Mr. Calculator do the hard work. So, in terms of a picture, probability that x is greater than x bar is greater than 105. On my calculator, normal CDF, 105 goes in, 10 to the 10th goes in, 100 goes in, but now instead of the 15, I'll put in the 15 divided by, then I'll pick up the square root of 25. The little arrow means I'm still within the square root as far as the cursor goes. I'll get out of that and I'll close up the parenthesis. Now, everything is in there and I'll hit enter and I get a probability of 0.04779 and change. Coming back over here, 0.0478 to 3 significant digits. Now, you'll note that there was quite a bit of difference in the two probabilities, and students usually wonder why that is so. Well, here's why. We'll make a little bit of a comparison. For our first example, with the individual score, the standard deviation was 15. For the sampling distribution, the standard deviation was 15 divided by the square root of 25, or 3. So you can see that the size of the sampling distribution standard deviation is much smaller. That means scores, in this case means, are much more closely compacted, much closer to each other. They're all bunched up together. Now, a picture helps us see why the two probabilities are so different. From the individual score, the area was 0.3694. The standard deviation was 15. Now, before I put up that last picture, I'm going to remind you that the probability distributions always have an area equal to 1 underneath that graph. So, when we look at the sampling distribution, that standard deviation being equal to 3 means values are much more concentrated around the true population mean. And you can see that the red area is significantly less than the black area, which is why the probability of a sample mean being greater than 105 was so much lower than the probability of an individual having an IQ greater than 105. It's subtle, but that is a super big and super important difference. So, we've reviewed the central limit theorem, we've looked at the implications, and you've seen some appropriate examples. That means I'm done with my presentation. I'm going to stop the sharing. I'm going to ask that you take a close look at the problems in 6.4. You really have to look at the language because you're going to see both kinds of questions together, A and B. So focus on the language. And remember to take and divide the population standard deviation by the square root of your sample size. Thank you, goodbye, and bring me your homework questions.